Members of the jury, the defendant is accused of making wild and extravagant claims about the universe. He claims to know how the universe came into being and how it is likely to end. You, the jury, have the task of weighing the evidence and deciding whether his theories are sound and acceptable or whether they are pie in the sky. Counsel will examine the defendant.
I swear by Almighty God that the evidence I shall give will be the truth, the whole truth, and nothing but the truth, as far as I can.
Your Honor, the defendant appears to doubt his ability to tell the truth.
Well, it's not as simple as that.
Well, how did the universe begin?
Well, it all started with the Big Bang.
Oh, the Big Bang.
Yes, a gigantic explosion. Allow me to illustrate. In the beginning, there was a great explosion. All the concentrated matter of the universe expanded outwardly as a searingly hot gas, eventually condensing to form the stars and galaxies we see today. These galaxies are still moving away from one another, as we'd expect particles to move after an explosion.
One moment, please. The fact that these galaxies are still moving apart is not ipso facto proof of a Big Bang.
But the further away a galaxy is, the faster it's receding. And if I run this in reverse, we see that the galaxies which are now far apart must once have been close together. When we work out just how far and how fast these galaxies have been traveling, we can then work backwards to discover when they were close together, when the Big Bang actually happened. And that, ladies and gentlemen, is how we know the Big Bang happened 15,000 million years ago.
15,000 million?
Well, between 10 and 20 billion years ago, yes.
Do you not accept that it could, in fact, have been a great deal older than that? I refer you to a paper of Professor Harrison from the University of Massachusetts, and I quote, perhaps, in fact, we occupy a non-standard universe, and the standard universe is a fiction, unquote. My Lord, Professor Harrison has produced a model of the universe that is 35 billion years old, and it still fits all the relevant data and observations. I put it to you that 15,000 million years is a very arbitrary figure.
Well, the exact age isn't important. What is important is the microwave background.
What is this microwave...
Background, sir? Well, you see, the Big Bang was a very violent explosion. All explosions produce a fireball, and the fireball from the Big Bang can still be found throughout the entire universe.
A ball of fire?
Oh, it's not hot anymore. It's the cooled down remnant of that cosmic explosion that we call the microwave background radiation.
Oh, yes.
Well, this background radiation is coming out as isotropically, smoothly, from all directions. But now its wavelengths have shifted from the very hot gamma range to the much colder microwave range, and what's more, it has exactly the spectrum we would expect it to have.
These are the measurements of the brightness of the radiation from the Big Bang at different wavelengths. It's a test of the color of the Big Bang radiation. You can see the points all follow a very nice pattern. Now, there's a prediction from the theory of the Big Bang that shows that the radiation should have the spectrum of a perfect radiator. Here's the theoretical curve. You can see that they really agree extremely well. You can hardly see the difference. All the points lie right on the curve.
Isotropically?
I beg your pardon?
Well, you tell the court that this radiation was coming at us smoothly from all directions, isotropically. Was this radiation originally given out by matter?
Yes.
The same matter which now makes up the stars and the galaxies?
Yes.
Then the matter in question is clearly not evenly distributed. Stars, star clusters, galaxies, and so on. This clumps of matter, they're supposed to be giving out smooth radiation. Surely that doesn't add up.
I see what you're getting at. Now, that was a problem, but it's been sorted now.
The defendant will answer the question. Smooth isotropic radiation from clumpy bits, stars and galaxies.
All right, I can best answer that by calling my second witness, Professor Smoot.
We were sure it's thermal radiation, and we'd measured its temperature to be 2.726 degrees to within a few thousandths. Our next task was to do an all-sky survey. Unfortunately, there are very many sources of non-cosmological radiation, including our own galaxy. To distinguish these, we made maps using receivers operating at 3 frequencies to give us color information. It was a difficult task because in some places the noise was 1,000,000 times stronger than the signal. It took us a year of observations and another year to analyze the data, but finally the maps at all 3 frequencies agreed. What we saw was that the sky was extremely uniform to a part in 100,000. That extreme smoothness supports the idea of a uniform plasma left over from the Big Bang. However, when we looked in more detail, we saw minute temperature variations, what we believe are reflections of the seeds that grew into the large-scale structure we see in the modern universe today.
I didn't understand a word he was saying.
So that's two independent pieces of evidence for the Big Bang. Point one, the recession of the galaxies.
Recession?
Hubble's word, my lord. And point two, the microwave background radiation.
And that is the summation of your evidence?
No, Your Honor, there's also Exhibit C.
Exhibit C?
A lump of shrapnel, my lord.
Shrapnel? Is there shrapnel floating about in outer space, then?
Well, in a manner of speaking, my lord, imagine an ordinary common or garden bomb.
Bomb?
When a bomb explodes, you get a fireball. I've dealt with that. But you also get pieces of shrapnel, like that. They're very useful for telling us what the bomb was made of, the force of the blast, etc. Well, the Big Bang was basically a cosmic bomb. I told you that it expanded suddenly in the form of light gases. And we can calculate just how much hydrogen, helium, and deuterium would have been formed in the first 3 minutes after the Big Bang. And so we can...
Just a minute, young man. This bomb, you're telling us it went off 15 billion years ago?
Well, give or take a few billion, yes.
A vague figure, one might say. And now you're talking about the first 3 minutes of the universe.
Well, it may sound incongruous, my lord, but it's nothing our known laws of physics can't handle. It's even been tested in a laboratory.
Here at the Rutherford Appleton Laboratory, powerful lasers are used to produce the temperatures necessary for nuclei to fuse together. That is, to provide sufficient energy for the nuclei to overcome their electric repulsion and approach closely enough for the strong force to come into play and to bind them together. Here, the reaction lasts less than 1/100th of a millionth of a second, but we can tell it happened because of the neutrons produced in the process. In order to apply what we learn here to conditions in the early universe, it's necessary to develop a theory capable of predicting the rates of the reactions and the type of particles produced in the reactions. We then go to experiment and measure the reactions by seeing the neutrons, protons, etc. produced in the reaction, and we find agreement with theory. The next step is to apply this theory to the early universe when the entire universe had temperatures of 100 million degrees, similar to the temperatures in these experiments. The final step is to combine our theory of nuclear reactions with the theory of the hot expanding universe and to predict the types of elements produced. This prediction is in remarkable agreement with the observation of elements in the universe today.
And that, my lord, is how we're able to predict the nuclear abundances. That, for example, 1/4 of the matter produced in the Big Bang would be helium, 1/4 of the mass. And if we look around today at the stars and the interstellar medium, we find just that. 25% of it is helium.
Silence in court.
Thank you. Convincing as that may sound, I can produce a witness who will cast some doubt on the reliability of the defendant's statement.
One can obtain the correct abundances of some of the light elements, particularly deuterium and helium-3 and helium-4, but this is only after one adjusts the parameters, and there is freedom in this. Moreover, the other elements which go with these elements in the nucleosynthesis process, namely the lithium and the beryllium and the boron, are not as easily explained in this theory. The strongest argument for the theory has been for many years the origin of the microwave background. But I would simply like to remind everyone that there are alternatives, and while they're not particularly popular at the moment, it is possible for other theories to be developed. And in practice, one of these has recently been developed by Hoyle and by Narlikar and me, and this is a theory based on the old steady-state cosmology, in which there never was a beginning, but in fact matter is created in bangs, in little big bangs, in the centers of galaxies and elsewhere. And there is much evidence that this kind of phenomenon is occurring in the universe.
Well,
My lord, I never suggested that absolutely every scientist believes in the Big Bang theory, but given the evidence, expansion of the universe, microwave background, and the nuclear abundances, 3 independent pieces of evidence, the Big Bang is the only reasonable explanation.
It is the function of the jury to decide whether the Big Bang model makes any sense. Counsel?
thank you, my lord. I would remind the court that the defendant is not only arraigned for his dubious claims as to the origin of the universe. Oh, no. He has also gazed into his crystal ball to tell us about the future. The future of the universe, he would have us believe, can be read in the stars. Well, I'm sure we're all most anxious to know what is to become of our beloved universe.
Well, that's all a matter of, matter.
Yes?
Could you expand?
Very good. Sorry, sir. Look, if I throw something up into the air, it's bound to come back down to the ground, right? If the Earth wasn't exerting a gravitational pull, it would keep on going up forever. Well, it's the same out there in space. Just as the galaxies are moving apart, their mutual gravity is trying to pull them back together, or at least to slow down their separation.
Oh, dear, oh, dear. Now you're suggesting that gravity is trying to pull them back together again. Will it succeed?
Well, it's certainly one possibility. It could happen that the universe will slowly stop expanding, and then we might have the opposite of the Big Bang.
And what would that be exactly?
A big crunch.
And that is your prediction for the future? Long term, I hope.
Well, it all depends on the matter. Only if the density of all the matter in the universe were greater than critical.
A big crunch certainly would be critical, in my opinion.
What I meant by critical density is what would happen if all the matter in the universe exerted just enough gravitational pull to halt the expansion. Any more than critical, and it would all pull back together again. Any less, and the universe will go on expanding indefinitely.
Expanding into what?
I don't know.
Oh, my lord, if I may continue. Is the density enough? Can you give us the measured value of the density?
Well, not really. You see, if we take the mass of all the billions of stars and galaxies, the matter we can actually see, it doesn't add up to much. About 1/100th of the critical density, in fact.
Could you repeat that value?
1/100th of the critical density.
That's not very much, is it? There is not sufficient matter in the universe to provide the gravitational conditions necessary to halt the continual expansion. Is that correct?
Well, as the song says, it ain't necessarily so.
Oh, Your Honor, this is ridiculous. The defendant gives evidence as to the continuing, unending expansion of the universe and then flippantly contradicts himself.
But I was only talking about the matter we can see. I haven't yet dealt with the matter we can't see.
Matter we can't see?
Dark matter, which doesn't give out any light.
Really? That is interesting. So, there is matter out there which we can't see. Such hidden obstacles must make space travel rather hazardous.
My lord, I would at this point like to call the Invisible Man.
Very well. Call the Invisible Man.
or rather, his picture, my lord.
Oh, picture of the Invisible Man.
This is a picture when he was appearing, so to speak, on stage. Because he's invisible, we can only tell that he's there because he's wearing clothes and bandages, making things move about. What we can see is enough to tell us about him. Well, it's the same with galaxies. Okay, we can only see the stars, but we can tell from their movements that gravity is acting upon them. In fact, more gravity than their neighboring stars could exert. So there has to be something more out there. The stars themselves are proof of that.
The most compelling astrophysical indication that dark matter really exists in the universe is found in the very rapid rotation of external galaxies. Galaxies rotate under the influence of gravity, just as planets in the solar system rotate around the sun under the influence of gravity. Galaxies in clusters swarm with respect to each other much more rapidly than you can account for directly. I've made measurements of the motions in the outer parts of our own Milky Way galaxy, and it too rotates more rapidly than we can account for directly. There seems to be no other way to explain these rapid motions than by postulating the existence of dark matter.
This invisible dark matter, do you know what it consists of?
You know, black holes, burned out stars, stars that didn't quite make it, like the giant planet Jupiter. All this extra matter takes us up to a value of between 1 and 5% of critical.
No more than that.
No, that's about as far as we can go with baryonic matter.
Oh, what matter?
Baryonic matter, atoms, nuclei, that sort of thing. If there were any more baryonic, normal matter, then the density of that matter during the first 3 minutes of the universe would have been too high. It would have altered the nuclear abundances. Oh. I mean, the stars wouldn't have the same proportions of elements as they do today. For example, deuterium, a form of heavy hydrogen.
But you still haven't accounted for more than 5% of the critical density. Yet you insist that the density in the universe must be critical. Where is it all?
Well, take heavy neutrinos.
Heavy neutrinos? I was rather under the impression that neutrinos had no mass whatsoever.
Well, they might have some mass, very, very, very small. But there are so many neutrinos flying around the universe that even a tiny individual mass would add up to a huge collective mass. I mean, it's possible.
Possible? Will the jury please note that what we have here is supposition and not hard fact? Is there any evidence for these heavy neutrinos?
No, not really.
No, not really. My lord.
There have been several attempts to measure the mass of a neutrino.
And they have not succeeded.
No, but heavy neutrinos aren't everything. I mean, there are exotic particles, for instance.
Exotic particles? Are you sure we're not straying into the realms of some bizarre fantasy?
Quite sure, my lord. You see, the high energy conditions of the Big Bang could have created special particles with qualities we don't yet understand.
And the evidence for these exotic particles?
We're still looking for them.
No evidence.
No.
So, of the matter required to achieve critical density, only 1% or so is visible, yes? 99% of the universe must be composed of invisible matter. Is that so? And yet you are claiming that this welter of dark matter includes either heavy neutrinos or exotic particles, or both, even though no experimental evidence exists to support these phenomena. I put it to you that your theory rests on things which cannot be seen and whose existence cannot be proven.
Does it have to be critical? If the universe is still expanding, then the density of mass in the universe need not be critical. So your attempts to prove that it is would seem superfluous, to say the least.
Good point, Your Honor. Except that really the density does have to be just about critical. It's very important, because of inflation, you see.
Oh, first recession, now inflation.
This is a different meaning of the word, my lord. You see, when the Big Bang happened, the universe expanded very suddenly and very rapidly before slowing down to its present rate.
And when did this so-called inflation take place? In the first 3 minutes of the universe?
No, less than that.
Oh, the first minute, the first 30 seconds?
My lord, inflation happened somewhere between 10 to the minus 35 and 10 to the minus 32 of a second after the start of the Big Bang.
10 to the minus 35 of a second. No, what's that in layman's terms?
Well, for example, 10 to the minus 12 is 1/millionth part of 1/millionth of a second. And we are talking about a period of time almost 1/millionth of a millionth of a millionth of a millionth of that. Put it this way, the forces of nature behave very differently at different energies.
In big laboratories, such as the Fermi laboratory where I work, we are able to accelerate particles to much higher energies than those in nuclear fusion. To do this, we need an accelerator several miles in circumference to build up the energy of the protons. The protons and antiprotons then collide head-on, releasing this energy into a shower of particles as predicted by the special theory of relativity. At very high energies, many particles may be produced, and their tracks are recorded in huge detectors. Just look at the number of particles produced in these typical reactions. In this tiny volume of the collision, we produce temperatures present in the universe a millionth of a second after the bang. And we can reproduce here on Earth, in this volume smaller than the size of a proton, the conditions present in the entire universe long before the elements were formed. What our experiments also show is how the strength of the different interactions vary with energy. Extrapolating this behavior to very high energies, far beyond the reach of present accelerators, we can predict that the strengths of the various forces come together at high energy. Based upon this simple idea, theorists can work out the way the entire universe behaved in the very moments after its creation.
Well, I still don't see what inflation has to do with your Big Bang and critical density and all that.
Then, Your Honor, I refer the court to the evidence of Professor Alan Guth.
At the start of inflation, the embryo for the entire observed universe is more than 1 billion times smaller than the size of a single proton. Inflation is very rapid. It lasts only for about 10 to the minus 32 seconds. But during this very brief period, this embryo expands to become at least the size of a grapefruit and possibly even something much, much larger. When inflation finally does end, the universe continues expanding in a coasting motion, which slows gradually due to the attraction of normal gravity. During the inflationary period, essentially all of the matter and energy in the universe are created. And the remarkable feature is that the matter that's created during this very brief period is created in precisely the right amount to establish the critical density. No matter how one begins, if there's enough inflation, the density at the end has the critical value.
Ah, so in other words, the density has to be critical. So there has to be an enormous amount of dark matter out there. Am I right?
Yes, my lord. You've got it. As Professor Guth states, without inflation, this amazingly precise value has to be regarded as simply a complete coincidence. With inflation, the value is inevitable. You see?
Yes, I do see. It's all beginning to make sense now.
My lord!
Oh, yes, do go on.
Thank you. Yes, inflation is a very useful, attractive idea, isn't it? But again, there is no evidence to prove it. It's just another in a string of fanciful, theoretical notions. My lord, if I could bring in the testimony of Professor Sir Martin Rees.
I believe we have good grounds for extrapolating the Big Bang idea back to the epoch when the universe was 1 second old and when the helium was made. This isn't proved beyond reasonable doubt, but I'd bet 90% on that being basically correct. On the other hand, when we go back still earlier to the inflationary era, one can't be quite so confident. That's because the basic physics is far more extreme and less well understood because we can't test it in the lab in the way we can test the physics of nuclear reactions.
So, even an expert witness such as Professor Sir Martin Rees cannot accept some of the defendant's wilder claims about the origins of the universe. My lord, I rest my case.
Does the defendant have anything more to say?
No, not just now, Your Honor. But we're learning all the time.
Very well. Members of the jury, you've heard the claims made by the defendant, and you have heard the evidence he has offered to support his theories. If you accept his view, then you must accept that our universe is some 15,000 million years old, and that it all began with an explosion, and that a process known as inflation took place within a fraction of a second after the Big Bang. What you must ask yourselves is this: is the defendant justified in promulgating such theories, and is the evidence persuasive enough to support them? I cannot advise you. I must ask you now to retire in order to consider your verdict.
Remarkable agreement with the observation of elements in the universe today.
I'd like to remind everyone that there are alternatives, and while they're not particularly popular at the moment, it's possible for...
And another year to analyze the data, but finally the maps at all three frequencies
Without
agree.
inflation, this amazingly precise value has to be regarded as simply a complete coincidence.
And the results of every experiment that's ever been done with these particles, and I mean every experiment, is in perfect agreement with theory.